Okay, so yesterday we reviewed position versus time graphs. Okay, we talked about what the slope represents on there. We talked about how you can analyze any graph to figure out what its slope represents. Today we did a few calculations and problem solving things to do with graphs using y equals mx plus b. And we did a few irregular graphs. That's what we ended with, was that one irregular graph. How to calculate distance, how to calculate displacement, speed, velocity, okay, in all of those situations, okay, hopefully which was all review from Science 10 for you, okay. Today is also going to be pretty much all review of Science 10 as we talk about velocity versus time graphs. On a velocity versus time graph, we can tell how fast and in what direction an object is going at various points in time. We could have a velocity versus time graph and a position versus time graph for the same motion. Would they look at all alike? If I had the same motion and I had a position versus time graph of it and a velocity versus time graph of it, would they look the same? No, they're going to look very different. Okay, because they're showing the same thing, but they're showing it from different points of view. Right? So case in point here would be these two graphs. Okay, graph on the left is a position versus time graph. Okay, from yesterday, what is that object doing? It's angled upwards and it's diagonal.
Moving at a fixed rate.
Right, it's moving at a fixed rate or at a constant velocity. Its position is changing by the same amount every time interval, constant velocity. Graph on the right is a velocity versus time graph. What is it showing?
Fixed rate.
Yeah, it's the same graph. Okay, or same motion, not same graph, sorry. It's the same motion. Okay, they are both showing an object traveling at a constant velocity. In fact, they are showing the same object. Okay, and we can prove it. From this graph, could I calculate the velocity of this object? Yeah, because I can use this. Okay, I know the y-intercept is 100 on this graph, so I know what b is. Okay, I can use that for y, it'll be 1400, and I can use 5 seconds for x, and I can solve for m. Everybody okay with that logic? Okay. So if I go m equals 1400 minus 100 divided by 5 seconds, I'm going to have 1300 meters divided by 5 seconds. I believe that's 260 meters per second. My mental math is okay. All right, everybody okay with that? Is that exactly what the velocity versus time graph is showing? Okay. I mean, here's 200, here's 250, there's 300. That looks like 260 meters per second to me. Okay. And it's showing that it's not changing. Okay. Now, here's how this could get tested. I throw a multiple choice question on your unit exam and I show you that graph. And I ask, what is happening in this graph? A, object not moving. B, object moving forwards at a constant velocity. B, object moving backwards at a constant velocity. D, accelerating. Okay? How many people would I catch on object not moving? About a third. Okay? I get about a third of people on average with object not moving because they look at that graph without looking at the axis and they see a flat line. And flat lines mean nothing's happening. Okay? And they just automatically go with not moving. But in fact, something's not changing here, but it's the velocity that's not changing. The object is actually moving. It's just moving at a constant velocity. So, what is the point of my rambling story? The point of my rambling story is always look at your graph so you know what kind of graph it is. Because these two things are the same motion, but they look very different. Okay? And we want to make sure we're analyzing the right kind of graph because we calculate different things from both types of graphs. Okay? So we need to make sure we're doing the right calculations for the type of graph we have. It's very easy to fall into that trap of, oh, it's the slope of the line, but it's not on this graph, okay? So we want to make sure we're analyzing the right kind of graph. Okay, could I calculate the displacement of the object from this graph, from the position time graph? Did we do that yesterday? We did, okay. Position or displacement is final position minus initial position. I can read that off of this graph very easily. Right? I would just go, all right, 1400 minus 100, just like I did on the top here, okay? And I would get 1300 meters positive. Could I calculate the displacement on this graph? Obviously not that way, right? That graph doesn't show me position, does it? Is there another way to calculate displacement that we've gone over? Do I have a formula I could use? Which one? Okay.
Time times velocity.
Yeah, I could use V equals D over T. Okay, if I use this formula here, V equals D over T, okay, I could solve for D. I just multiply both sides by T. On this graph, I can read the time, 5 seconds. I can read the velocity, 260 meters per second. Okay, I can absolutely calculate the displacement on that graph. Very differently than the first graph, but I can still do it. Right? Now, this is probably something that you memorized back in Science 10. On a velocity versus time graph, if I want to calculate the displacement, I calculate the what? Under the line. It's the area, yeah, under the line. Okay? Did I just do that here? If I go T times V in order to get D, am I going base times height? Okay? The reason that works is because you're multiplying the base time by the height, average velocity. In this case, because the velocity doesn't change, it's just a rectangle, so it's just base times height. Okay, everybody all right with that? So if you memorized back in Science 10, the area under the line, good-ish, okay? But I want you to understand why that works, okay? Because we're going to be using that a bit more today. Okay, what would a graph that looked like this mean? What's that object doing?
Accelerating.
That object is accelerating. Okay, how do we know that? Well, at time 0, it's going 100 meters per second, and at time 5 seconds, it's going 400 meters per second. It seems to be going faster. Okay, simple interpretation of the graph, right? That doesn't require me to memorize anything. It just requires me to look at the graph and go, the velocity changed over time. Okay, now, in Science 10, you learned about this formula. That acceleration is the change in velocity divided by time. Okay? That formula comes from this graph. Okay? And it looks just like this. Is that by accident that they look alike? On this graph, the slope of the line is the acceleration because it tells you the rate you're changing your velocity by. Okay? Just like on any graph, the slope is how quickly y changes as a function of x. On this graph, how quickly y changed as a function of x was velocity, change in position divided by time. On this graph, it's change in velocity divided by time. Okay? That's that analytical skill I want you to have. I don't want you to memorize what the slope is. I want you to be able to look at this and go, all right, if I calculate the slope, what I'm really doing is taking one velocity, subtracting another velocity, and dividing by time. That's that formula. Okay, the slope is acceleration. Okay. What's the slope of that first line? the horizontal one? What's the slope of that line? Doesn't have a slope, right? It's horizontal, flat. So the slope is 0. Is that also because it's not accelerating? It's traveling at a constant velocity, right? Okay, these are all things that I could put in a multiple choice question, right? I could throw that first graph with the horizontal line on there and go, what's the acceleration of this object? Okay, people would go through all kinds of trouble to try and calculate something instead of just looking at the graph and going, no acceleration there because the velocity's staying the same. Okay, that's, again, don't memorize, I want you to analyze. Okay, every graph is different, but every graph can be analyzed. Okay, when we calculated the displacement for this horizontal line, we just went base times height. We calculated the area under the line. Can I calculate the displacement for the diagonal line? I mean, we just established that I can calculate displacement this way with that formula. But it was easier there because the velocity was constant. Can I still do that when the velocity is changing? When we write this formula, is it really this? Is that the true meaning of that formula? Okay. Can I find the average velocity for that diagonal line if I know it increases from 100 to 400? Right? How do you calculate the area of a triangle?
Base times height divided by 2.
Base times height divided by 2. If I divide the height of this triangle by 2, will that tell me the average velocity of that object? It will, because half of the time it'll be going slower than that number, and half of the time it'll be going faster than that number. That makes halfway up the average. That's why that formula works. Okay? We're not doing anything tricky. Okay? We're not having to memorize that it's the area under the line. We just have to remember that I can calculate displacement by taking the time and multiplying by the average velocity. In this case, that's the height of the triangle divided by 2. It's the maximum velocity divided by 2. Okay? Assuming it's nice and uniform like it is there. Right? Everybody okay with that? Okay. Does it get a little crazier if you start getting lots of shapes? It does. Okay. It gets a little crazier because you got to draw all the shapes and you got to find all the areas. But in the end, all you're doing is taking the average velocity and multiplying by time every time you do that. Okay? It's why that method works. All right, so we can calculate acceleration off of a velocity versus time graph. We can calculate displacement off of velocity versus time graph. We can calculate average velocity off of a velocity versus time graph. Can we interpret velocity versus time graphs as well? Just by looking at them, can we tell what's going on? We can. Okay, and all of those things are things that you've done already in Science 10. Okay, you told me the first line, the horizontal line, traveling at a constant velocity. You told me the second line, it's accelerating. Okay, what would this line be? Accelerating negatively. Yeah. Okay. Everybody all right with that? Okay, so this is a velocity versus time graph of a person running a race. Okay, so the gun goes off, and what does the person do at the very beginning? Does their velocity change? Okay, so what do we call that? Reed, what do we call that?
Accelerating.
Call it accelerating. Okay, so for the first part, they're accelerating. And then, like what happens in any race, you can only accelerate for so long. And then it doesn't matter how hard you push, you simply can't run any faster. You reach your top speed. And for the next few seconds, they run at that speed. Okay, as fast as they can possibly go. What happens after that?
Start slowing down.
Yeah, they start slowing down. And in fact, they actually come to a,
Stop.
how do I know that?
The line ends at 0.
Right, it goes down to 0. It goes down to where my velocity would be 0, and thus I would be stopped. Okay? They stop pretty fast. Okay? But they stop. Is this person super fast? Okay. Looks to me like their top speed's about 8 meters per second. That might sound impressive, but that's actually not all that fast. Okay? Usain Bolt, at his maximum speed, almost 17 meters per second at his top speed. Okay? So, if you're, a high-level athlete, graphs like this are actually useful in your training. Okay? They would make graphs like this of professional hockey players so they would know what their acceleration looks like and if they need to work on their power or if they need to work on their endurance or if they need to work on whatever. Okay? Their graphic information can tell them that. This is actually a huge tool in all kinds of performance and sports science. Okay? Looking at graphing people's speed, graphing people's position, okay, can tell you a lot about where their strengths and their weaknesses lie. Okay? If you were, let's say, analyzing Usain Bolt, because I coached track for a really long time, okay, if you're analyzing Usain Bolt's graph, okay, his graph would tell you something very important. So his velocity versus time graph would obviously go up to 17 meters per second, okay? But this is what it would show you. Okay? His competitors would have graphs typically that look like this. What does that tell me Usain Bolt's strength is?
Top speed.
Top speed. Nobody can touch that guy at his top speed. I mean, he's 6'7". Okay? He's got legs up to his neck. Okay? And he can make them move really, really fast. Okay? That gives you incredible top speed. Okay? When this guy is running at his top speed, he goes from the window across the hall and almost to the other side of the chemistry lab in 1 second. Okay? He can finish a 100-meter race in 33 strides. Okay, so imagine when he's at his top speed, how far he covers in 1 stride. Dude has an amazing top speed, but his acceleration sucks. Okay? He has to unfold himself at 6'7" from the starting blocks. It's not, I mean, when you're that tall, your power is going to be lacking. Most other sprinters are very powerful, kind of shorter. Okay? And so they would have a lot greater acceleration because they would have greater power. But their legs are shorter, so they don't reach as high a top speed. Okay? It's why if you ever watch a race that Usain Bolt is in, he never leads until the end. Okay? Everyone else is in front of him. He kind of steps up out of the blocks and then just starts to run. Okay? Whereas everybody else is powered and exploded out of the blocks. Okay? And they're all doing this the whole race. Because they know he's going to reel them in and pass them because his strength is his top speed. Okay? That's the kind of analysis you can do in a real world situation from a graph. Okay? If I'm training this guy and I know he's got to run against Usain Bolt, I'm going to be like, your acceleration's awesome. We got to make you faster. Okay? You've got great power, but you're always going to get caught at the end. We have to increase that top speed. We know we can't match his. No one's going to be that fast. But if we can make you just a little faster, you might be able to hold him off, okay, until the end of the race. Okay? That's sports science. That's how the stuff we're doing, okay, can be useful. Okay? Sort of make sense? All right. right, so for looking at a velocity versus time graph, okay, obviously the thing we can read, instantaneous velocity. We can always look at the graph and know, well, at this time, the object was going this fast and in this direction. And at this time, this fast and in this direction. So that's what we can read directly off. And we can infer what type of motion is going on from the shape. Okay, if it's going up, they're speeding up. If it's going down, they're slowing down. If it's flat, they're running at a constant velocity. Okay, and we also know this little trick from Science 10. Okay, the area under the line, or we shouldn't say under, but between the line and the x-axis is going to give you displacement. Okay, so I would say, rather than under, I would say between. And I'm going to show you why in a minute. Okay, between the line and the x-axis, okay, sorry, between the line and x-axis. Okay, here's why I say that. If I have a graph that looks like this, okay, where it's in the positives and then it drops down into the negatives, okay, I don't want to calculate the area under the line. I want to calculate this area and that area between the line and the x-axis. I only say that because I've encountered people who actually calculate the area under the line and it's not the same. So it's always between the line and the x-axis. All right, and really all we're doing there is going average velocity times time. Average velocity times time. Okay. All right, I'm going to go over a couple of examples here. Okay, for this graph, here is what I would like you to do, just for run 5. Okay, so that's the steep orange line right here. Okay, for run 5, I would like to know the acceleration. And the displacement to 0.2 seconds. Okay, those are the two things I would like you to find. For run 5. What's the acceleration for run 5?
7.61.
Yep. Okay, did I have to do any calculating for that? No, I just had to recognize that the slope on this graph is the rate at which velocity changes. That's the definition of acceleration. Okay? Acceleration is the rate at which you change your velocity over time. So, since this is a velocity versus time graph, the slope is telling me how quickly the velocity changes over time, so the slope is the acceleration. Okay, didn't have to memorize that, just had to analyze it. This is velocity, this is time, how steep the line is, this is how quickly the velocity changes. That's acceleration. Okay, everyone follow me there? All right, so you didn't have to do any calculating there, okay? And it would have been pretty difficult to actually do any because you don't really have any data you can use, because I made the graph impossible to actually get data points off of. All right, now, for the displacement part, okay, remember that we're only going to 0.2 seconds. So we're only going this far. Okay, I'll give you a few more minutes on the displacement for run 5. Right, so we looked at this before and we said you can calculate displacement by calculating the area under the line. All right, for the orange line, I'm going to use red because I don't have orange. Okay. That would mean that I would have a rectangle underneath a triangle. Agreed? Those would be the shapes that would be underneath that orange line to 0.2 seconds. Now, if I want to calculate the area of that rectangle, I know the base is 0.2 seconds. What's the height of it? wouldn't the y-intercept be the height of that rectangle? Right? It tells me that that's where the line starts from, so that's where my rectangle goes to. Right? That would be the height, and I would have 0.2 on the base. Right? So I can do the rectangle here. It's going to be the velocity initial, which is 0.285, times 0.2 seconds. Okay, so 0.285 times 0.2, base times height for the rectangle. All right, so that part's going to be 0.057 meters. Okay, now for the triangle, I know the base. The base is still 0.2 seconds. How do I get the height of that triangle? Do I have the equation for the line? Can the equation for the line tell me what y is at 0.2 seconds? Pretty sure it's set up to calculate y if it's given x, right? And x is 0.2. So to get the height of the triangle, I would just go y equals 7.61 times 0.2, okay? And then I actually wouldn't even add on this 0.285. I only want the height of the triangle. If I add on 0.285, that gives me the distance from the x-axis to there. I only want the height of the triangle. Would you agree? Everyone follow what I mean there? If I add on the 0.285, what I calculate is this whole height here. I don't need that. I only need the height of the triangle, so I don't even want that 0.285. I'm just going to do this. Okay? 7.61. Okay, so now I have the height of my triangle. Okay, I didn't add on the 0.285 because I only want the triangle and not the full distance. Okay, and now if I do that number, height times base divided by 2, okay, I should have the area inside that triangle. Agreed? Okay, so I just calculated this here to be 1.522 meters per second. That's the change in velocity. Okay, so not divided times. And divide that by 2. All right, so 0.1522 is going to be this one. And that makes sense. It's bigger than the rectangle underneath, so that's an okay number to use. Okay, now what do I do with those two numbers? Just add them together. Now do I have the total area underneath the line? Okay, that's I mean, you did a few of those like that in Science 10. I know I made my Science 10s do that on their one lab. Okay, but I'm going to show you a trick that's going to make it a little easier. Okay, rather than going through all of that work, we're going to learn next week probably, okay, about some other acceleration formulas. So if everybody can take out their formula sheet right now, you're going to find this formula on your formula sheet. Okay, now I want you to think about what I did in order to get the area of those two shapes. Okay, to get the area of the rectangle, I took the y-intercept. The y-intercept is also the initial velocity of this cart. Would you agree? And I multiplied it by time. I'm pretty sure the first part of that formula calculates the area of that rectangle, doesn't it? And then when I calculated this area, I took 7.61, the acceleration, okay, and I multiplied it by time. And then I did this all again. I went this times time again, time squared, and then I divided it by 2. Same as multiplying by 1/2. This gives me the area of the triangle every time. Okay, is that way easier than doing geometry? Well, it's still doing geometry. It just doesn't feel like doing geometry. Okay, that formula is derived from doing that. Okay, remember we talked about yesterday how all the formulas we use, they're all derived from a graph. Here's another one. Okay, that one calculates the displacement by figuring out what the area between the line and the x-axis is, okay, for your object. Okay, so keep that formula in mind. It can help you with this stuff. Okay. All right. I'm going to give you guys a little break here. Let's say 5-minute break, and then I'm going to have you do a couple other things with this graph. Okay, so put this somewhere in your notes. Okay, that little trick, because that'll come in handy. Okay, looking for how fast, okay, what is the velocity of each one of those carts after 3.2 seconds? All right, how do we go about doing that? Which axis is velocity on? It's on the y-axis. Did I give you an x value? Okay, that's the analysis we need to do. Okay, we need to look at, okay, what was I asked for? Is it on my graph? What axis is it on? Okay, well, I'm asking you how fast. That's a y value. This is in meters per second. This is time in seconds. I gave you an x value. For each one of these, it's the same calculation with their equation. All right, so for the blue one, it's going to be y equals 1.28 times 3.2 plus negative 0.0885. Okay, so for the blue car, after 3.2 seconds, it'll be going 4.0 meters per second. Okay, for our red cart, okay, so y will equal 2.4 times 3.2 plus 0.0333. All right, so that's going to be 7.7 meters per second. Okay, for our yellow one, okay, same calculation, but with its numbers. So 3.5 times 3.2 plus negative 0.197. All right, so it'll be going 11 meters per second. Okay, am I doing my significant digits okay here? I am. Okay, all of my answers have had 2 significant digits, okay, except for this first one. That had 3, that had 3. This should have had 3. It should have been 4.00. All the rest, okay, 2.4, 3.5. This one should have how many? 1 and done. Okay, all right. So if we're looking at the blue line, sorry, not the blue line, the green line. Okay, so for the green cart, y is going to equal 6 times 3.2 plus negative 0.182. All right, so 19. Actually, that one's going to be 2 times 10 to the 1 meters per second, because that one only has 1 significant digit. And then for our last one, we'll be back to 3 significant digits for that one. Because I don't have orange, I'm going to use red. I can do this. Orange. Okay. That probably won't work. Orange. We're just going to use red. Red. Anyway. Okay. So it'll be 7.61 times 3.2 plus 0.285. Oh, actually, no. All of these should have, well, that one should have 1, but all the rest should have 2, because what did I multiply by? 3.2, that's only got 2. Okay, plus 0.0885. Oh, no, sorry, plus 0.285. Okay, 24.6, so 25. Meters per second. Okay, so in the end, was the math of that question very difficult? No, you're just plugging 3.2 into every single one of those formulas and not having to manipulate anything, but it's getting there. Figuring out that that is what you're supposed to do, that's the tricky part. Okay, and that involves, again, that skill I've been talking about all day and all day yesterday, graphical analysis. What's on my graph? How do I get what the question's asking for using what's on my graph? Okay, and guys, here's a little tip. If I ever give you a graph that has the equations on it, you should use them to answer as many questions as possible. Okay, I wouldn't give you that equation if I didn't intend for you to use it. Okay, all right. Okay, got an irregular graph here, okay, and it's for a snowmobile, an incredibly fast snowmobile, apparently. Like, I wouldn't ride that snowmobile. 80 meters per second is really fast for a snowmobile. Like, you're outrunning an avalanche straight down a mountain fast. Okay, so here's what I want you guys to do. I want the average, actually I don't want the average velocity. Let's just go with, I want the acceleration during each interval. Okay, during each interval, so this would be segment A, this would be segment B, this would be segment C, okay? And overall, and I would also like the total displacement. Okay, so average acceleration during each of the segments and over the whole trip, and the total displacement over the entire trip with that irregular graph. Okay, let's just look at the acceleration for each of the 3 parts here. Okay, for part A, I can use this formula to get the acceleration because I know VF is 40, I know VI is 0, and I know that that takes 20 seconds. All right, so for this part here, it'll just be A equals 40 minus 0 over 20 seconds. Okay, so 40 over 20 is 2 meters per second squared. Okay, what's the acceleration in part B? 0, traveling at a constant velocity. Okay, so that part's 0. And then for part C, okay, same formula. Okay, A is going to equal VF, which is 80, okay, minus the initial velocity, which is 40, and that takes 10 seconds. Right, so 40 over 10 is going to be 4 meters per second squared. Okay, so that's what you should have got for the 3 accelerations. How many people are done with the displacements? Okay, I'll give you a couple more minutes and then we'll look into that. So there's 2 ways to calculate the total displacement here. The geometry way, okay, which probably a lot of you did, where you went, all right, I need the area of this triangle, I need the area of like this whole rectangle here, and this triangle up here. Okay, totally fine to do it that way. Okay, so for this one here, we'd have 20 on the base, so 20 times 40, okay, and then divided by 2, All right, so 800 over 2, let's just do this with my calculator so I get it right. Okay, so 20 times 40 divided by 2. All right, so that's going to be 400 right there. All right, and then for B, that whole, well, actually, it's not just B, it's also the rectangle under C. Okay, we're going to do the whole thing there. From 20 to 60 is 40, and it's 40 high. So 40 times 40, that should be 1,600 meters. And then this little triangle up here, okay, it's got a height of 40 and a base of 10. 40 times 10 is 400 divided by 2, okay, is 200 meters there. Okay, so we're looking at 2,200 meters, doing it the geometry way. Okay, everybody all right with that? Is there another way to do it? Could I use that third formula? I'd have to use it 3 times, but I can use it. Okay, I can go, all right, in this first section, okay, VI is 0, so that would be 0. And then I would just go 1/2 times the acceleration I calculated earlier, okay, times the time squared. Probably will get the same number there. So if I go 0.5 times 2 times 20 squared, okay, look at that, I get the same number. Okay, for this part here, there's no acceleration, so this part would be 0, and I'd just be going base times height, all the way across for that. Okay, actually, it wouldn't be all the way across, it would just be for this part here. Okay, so for that, I would go 30 times 40. Okay, so that's going to be 1,200. Okay, so I get this box here to just be 1,200 this time. And then I do this part. Okay, I know what VI is. VI is 40. I know the time is 10 seconds. Okay, so I can do the 1/2 AT squared part for that. Okay, so I would have 40 times 10 plus 0.5 times the acceleration I calculated, 4, okay, times the time, 10 squared. Okay, so I get 600 for that. Okay, I'm pretty sure if I add all those together, I still get 2,200. Either way works. Okay, it just depends on which way you feel comfortable doing. All right. Okay, does that ring, other than the new formula, does the geometry part ring a bell from last year? Okay. Okay, just looking at this graph here, just doing graphical analysis. What's that object doing?
Decelerating in a positive direction.
Yeah, it's slowing down. You're accelerating in a negative direction. Either way, okay, it is slowing down. This is a position versus time graph. Okay, the amount of distance covered every time interval is decreasing. Right? It's getting to be flat. Okay, so that object is going slower and slower. Okay, that could easily be a multiple choice question on a quiz or a test. Okay, no, not that one. Where's the one I want? Come on, there it is. Okay, this graph here, okay, bird starts flying south, and then its motion looks like this. Okay, this is a velocity versus time graph. Okay, for part A here, okay, actually, you know what? I'm going to have you guys answer these questions using this graph here. All right, answer those 3 questions. Okay, it won't take you very long. I'll give you a couple minutes on that, and then we'll talk about it. Mostly here, I'm worried about C. I really want to talk that one over to see how many people get it. Okay, so for part A, is the acceleration positive, negative, or 0 for each section? In section A, it is negative. Okay, section B, it's 0. C, negative. D, E, and F, 0. Okay, now calculating the actual value simply means using this formula here over and over again. Okay, so for part A, that's going to be -4 minus -2. So -2 divided by 1 second is -2 meters per second squared. Okay, and then for C, that takes again 1 second, and it goes from -6. So -6 minus -4 is -2. It only takes 1 second, -2 meters per second squared. Could I have saved myself work right there? Could I have just looked at the graph and gone, those two lines have the same slope and not done any work? I absolutely could have. Okay, that's where a little visual analysis can save you some time. Okay, I just look at this and I know those two things have the same slope, I'm done. Okay, if they have the same slope, they have the same acceleration. All right, then for this section here, we go all the way up to +6. So we'll have 6 minus -6. Okay, and that takes, it goes from 7 to 9 seconds, so over 2. All right, so we've got 12 over 2, so that is going to be positive 6 meters per second squared for that part there. Right, and then the other one is 0. All right, most important part of this question. At what time does this bird change direction?
7 seconds.
7 seconds. Okay. From how many people thought it was right here? You don't have to admit. You can answer yourself that. But how many people thought it was right there? Okay, it's okay. That's where the acceleration becomes positive. But this bird's velocity is negative. All along this part, well, I went off the line because I looked away. Okay, it's negative until it gets to right here at 7 seconds. At that time, its velocity is 0. I don't know about you, but birds tend to fall out of the sky if their velocity is 0. So I don't know what was really going on there in terms of reality, but okay. So the bird's velocity is 0 right there, and after that, its velocity is positive. Okay, again, this is a velocity versus time graph. It tells us how fast and in what direction the object is going. Its velocity is negative until 7 seconds. It may be accelerating the other way, but it isn't going the other way until 7 seconds. Does everyone follow the difference?
Isn't that 8.5 seconds?
Sorry, 8.5 seconds, sorry. I was so excited about the question, I just got to get to myself. Yes, you are absolutely right. Coder is needs more coffee or something. He's struggling today. Okay, yes, sorry. 8.5 seconds is where that change in direction happens, not at 7. Sorry. And I said right after I said, at 7 seconds, it's a good thing we're recording this for posterity so everyone can see my mistakes. Okay, so right here is where it changes direction. Here's where the acceleration becomes positive. Yes, at 7 seconds. Okay, but the velocity doesn't become positive until 8.5 seconds. And after that, it is actually moving in a positive direction. And it's still accelerating in a positive direction. Okay, so that can be the kind of thing that happens. If I threw something up in the air, that graph would look similar to that. Okay? Its acceleration would be negative the whole time, but it wouldn't actually start moving downwards until it had gotten to its maximum height and stopped for an instant and then started to fall. It would be kind of the opposite of that graph. Okay? It would look like this. Okay? It would be moving in a positive direction, positive direction, positive direction. It would stop for an instant and then be falling in a negative direction, and the slope of that line would be the acceleration due to gravity. Okay? It's strange to think of it that something could change direction, but its line not appear to do anything. Its line, remember, is showing its acceleration. Okay? It's also showing its direction if you look at it the right way. Okay? Everybody with me there? Kind of a weird one, but that's kind of one of those interpretation questions that can certainly come up. Okay, a couple of things for tomorrow. Okay, tomorrow we're doing our first lab. Okay, hopefully everyone's got the SparkView app ready to go. Okay, we'll start class with just, I'll get you the Chromebooks, we'll get going on things, get the pre-lab stuff done. Okay, if you're really working hard and paying attention, you shouldn't have too much to do outside of class for homework. Okay, it won't be due until after the break, obviously, to give you some time to work on it, come see me for help. So I'm thinking like the Wednesday at the earliest after the break, maybe the Thursday, we'll see. Okay, and then obviously Friday is your quiz, okay, and it's on graphing and V equals V over T. Okay, so again, make sure you have a look at those practice quizzes if you are looking for something in terms of those types of things. Okay, all right, I'm sure they're going to be coming on to the Angelus here in a minute. So, okay, we'll stop there.